We may have to rewrite all the textbooks on the beginning of the universe. It takes many billions of years to create a galaxy like the Milky Way with 100 billion stars, which is many billions of years old. But the James Webb Telescope has identified 6 galaxies that exist 500 million years after the Big Bang and are up to 10 times larger than the Milky Way. Now there is no turning back. The James Webb Telescope has discovered one of the oldest galaxies of all time, and it's so huge and luminous that it cannot possibly be a galaxy from the early universe. The U.S. physicist Michio Kaku suspects that we are now at the beginning of a new era and a new physics. This new physics could give more room to models such as string theory and the multiverse, and finally bring us the solution to the Hubble tension. Michio Kaku is right when he laughingly comments on the latest discoveries of the JWST. Webb showed us galaxies that supposedly existed in the early universe, but they are so large and so evolved that they must have been formed before the Big Bang. There has already been evidence in science that the universe as we imagine it does not completely match reality. You may have heard of the Hubble bias, a measurement error in determining the expansion rate of the universe. This problem has been known since the 1990s, and no one has been able to solve the mystery. Now Webb keeps showing us that there are other things wrong with our cosmology and astrophysics. We can be wrong on many levels. The Big Bang could not have happened 13.8 billion years ago, when only 250 million years later galaxies, which, as Michio Kaku notes, are larger than our Milky Way, were already moving through space. According to our current understanding, galaxy evolution is a complex process that takes billions of years to produce galaxies like our Milky Way. Webb found dozens of these ancient, beautifully shaped and large galaxies. Each of them presents a mystery to scientists. But not only that, Webb also showed us images of supermassive black holes that contained more than 1 billion solar masses just 500 million years after the supposed Big Bang. All these observations show us that our scientific understanding was wrong, and the launch of the James Webb Space Telescope triggered one of the biggest crises in modern cosmology. Galaxies 10 times the size of the Milky Way, laughs Michio Kaku, pointing out that some newly discovered galaxies look 10 times the size of the Milky Way. The popular American astrophysicist is one of those scientists who have long pointed out that there are serious gaps in our science. His theories, which intended to connect quantum field theories with the astrophysics of great phenomena like stars and galaxies, were not taken seriously in conservative scientific circles. It is these conservative camps that are in big trouble now, as their rigid views of the cosmos and their understanding of the evolution of matter and the Big Bang are beginning to waver. Instead, we get new physics, and thanks to the Webb, we can discover completely new aspects of our universe. They certainly can't say they didn't know anything, because in addition to the Hubble telescope, even before Webb, there were several other signs that the old idea of the Big Bang and expansion could not be completely correct. Even the old Hubble Space Telescope is said to have found suspicious points of light in the early universe. One of these discoveries was a galaxy called Galaxies 3. Hubble detected the galaxy only as a very faint point of light, which was undoubtedly there, but did not allow a more detailed analysis. Only Webb lit up the darkness and looked back at the Galaxies 3. It turned out that this light was actually emitted from an old galaxy. Under Webb's keen eye, the galaxy showed a redshift of Zal 9.3, which means only that we are looking at a galaxy that existed only 510 million years after the Big Bang. This means that Galaxies 3 is also a primordial galaxy, much more massive and mature than expected for its age. There are also some anomalies in the galaxy that give scientists food for thought. It has a strange shape with 2 bright spots that reveal its 2 dense cores. This suggests that we are actually looking at 2 galaxies and experiencing a merger of galaxies in what is thought to be the early universe. A merger of two primordial galaxies in the early universe would not be unusual, but even if we look at the two galaxies separately, they are too large and too advanced to be true galaxies in the young cosmos by our old standards. Galaxies take billions of years to reach this maturity, but we see the galaxy as it was 510 million years after the Big Bang. The galaxy is dominated by young, bright stars, and scientists have found specific elements like silicon, carbon, and iron that indicate older stars. These elements are not typical of first letters. They formed only after many epochs of stellar evolution. This fact also argues against seeing a young galaxy here. As you can see, nothing can be right, and scientists have not yet found a solution to the problem. The discovery of old stars suggests that stars formed earlier and enriched the universe with metals more quickly. The old stars in Galaxies 3 may also indicate that the galaxy matured chemically faster than previously thought, or that we may be wrong about the age of the universe. This is where the excitement of Hubble comes into play. Is expansion wrong? Did you know that the expansion of the universe has never been fully proven? The idea that the universe is expanding is a theory for which there was a great deal of evidence, but the theory soon ran into problems. Expansion is one of the cornerstones of our modern cosmology. In the 1920s, it was like a revolution, because Webb is revolutionizing the way we see the world today. Let us consider for a moment how this notion arose, what evidence supports it, and what contradictions or inconsistencies it contains. The first evidence of the expansion of the universe came from the American astronomer Vesto Melvin Slipher, who in the 1910s studied the spectral lines of galaxies and found that many of them were redshifted. This showed that these galaxies are moving away from us. However, a decisive breakthrough occurred in 1929 when Edwin Hubble, also an American astronomer, discovered the relationship between the distance of galaxies and their escape velocity. Edwin Hubble used the Doppler effect to measure the speed of galaxies and found that distant galaxies are moving faster than us. This led to the formulation of Hubble's law, which states that the speed with which a galaxy recedes from us is proportional to its distance. This law has long been considered the first clear evidence of the expansion of the universe. Besides redshifts, there are other evidences of the expansion of the universe. The cosmic microwave background (COM) is the background radiation of the universe that originates from the age of the universe of approximately 380,000 years. It was discovered in 1965 by Arno Penzias and Robert Wilson. The uniform temperature distribution of this radiation in all directions indicates that the universe was once much denser and hotter and has been expanding ever since. Further evidence was the so-called Big Bang nucleosynthesis, according to which the abundance of light elements such as hydrogen and helium formed in the early universe is consistent with predictions of an expanding universe. Despite this evidence, there are also contradictions and unresolved questions about the idea of expansion. The most interesting of these is the Hubble stress. The Hubble tension refers to the difference in the values of the expansion of the universe when different methods are used. One method of determining the Hubble constant uses satellite observations of the COM-E. The measurements were made with, among others, the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope. These measurements always lead to a Hubble constant of about 67-68 chems per megaparsec. Another method uses so-called standard candles, whose light provides specific points to measure distances and speeds in the universe. Scientists especially use Cepheids and Type 1a supernovae as such standard candles. Cepheids are pulsating stars whose brightness is related to their pulsating period. A Type 1a supernova has a standardized luminosity. By measuring their apparent luminosity, distances can be determined and linked to redshifts to calculate the expansion rate. This method gives a higher Hubble constant of about 73-74 chems per megaparsec. Several explanations for this discrepancy have been proposed in the past. There may be systematic error in measurement methods or assumptions, resulting in distorted results. Many scientists suspect a misunderstanding in the theories of dark matter and dark energy. Both are said to make up most of the universe, but we have not yet been able to measure or recognize them, so we know very little about the actual properties of either. Previously unknown aspects of dark matter and dark energy may explain the tensions. According to James Webb's current observations, scientists even suspect that dark matter and energy can change their properties, making them physically unmeasurable or quantifiable. If this is true, we will probably never be able to scientifically describe the universe as a whole. However, there are other explanations for the Hubble tension. Conventional candles can be affected by their environment and thus ultimately are not reliable measurements. Currently, it seems that we are moving towards a new physics that will bring new insights and models. The expansion, or rather the retreat, of some regions of the universe is certainly not a lie, but a clearly observed fact. However, it is currently unclear whether the entire universe is actually expanding and constantly receding. Observations of regions of slower expansion and phases of growth in the speed of expansion rather suggest that the entire universe is not expanding uniformly, but only those regions that are directly visible to us. This could mean that we are facing an even more complex cosmological model than previously thought. James Webb's results provide more clues about what the universe is really like. Certainly, one of the most interesting observations of the Webb Space Telescope was the discovery of James 11. This record-breaking galaxy is only 150 million years younger than the Big Bang and shows us more about the early universe than ever before. James 11 looks the same as it did 13.3 billion years ago and is full of mysteries. Images taken by the Webb Space Telescope suggest that James 11 is even more advanced than its age and may therefore provide clues to alternative cosmological models. The stars in this galaxy appear to have formed faster and are older stars than expected. This observation supports the idea that the first stars were born in the universe much earlier than our standard model predicts. In addition, James 11 contains a lot of dust, which is surprising for such a young galaxy. Dust is usually produced by dying stars, so finding so much dust in such an old galaxy could mean that stars formed and died in those galaxies faster than expected. What does it all mean? It's time for a new physique. In a way, we can already feel curiosity about the first alternative models. Quantum field theories are increasingly incorporated into cosmological models. The problem is currently still in their practical evidence. Although this new era is still in its infancy, practical demonstration of quantum effects throughout the universe may be the first to follow James Webb. Webb will provide us with more evidence over the next few years, so we can hardly wait for the new discoveries to come. In addition to James Webb, the Euclid Space Telescope launched on July 1, 2020. It could give us important answers. Euclid's mission is to give us more information about dark matter and dark energy to explain the mystery of the universe. Until then, however, scientists have a lot of work to do to discover new physics.